HierSpeech++, bridging the gap between semantic and acoustic representation of speech by hierarchical variational inference for zero-shot speech synthesis. Large language models, LLM-based speech synthesis, has been widely adopted in zero-shot speech synthesis. However, they require a large-scale data and possess the same limitations as previous autoregressive speech models, including slow inference speed and lack of robustness. This paper proposes HierSpeech++, a fast and strong zero-shot speech synthesizer for text-to-speech (TTS) and voice conversion (VC). We verified that hierarchical speech synthesis frameworks could significantly improve the robustness and expressiveness of the synthetic speech. Furthermore, we significantly improved the naturalness and speaker similarity of synthetic speech, even in zero-shot speech synthesis scenarios. For text-to-speech, we adopt the text-to-VC framework, which generates a self-supervised speech representation and an F0 representation based on text representations and prosody prompts. Then, HierSpeech++ generates speech from the generated vector F0 and voice prompt. We further introduce a high-efficient speech super-resolution framework from 16 kHz to 48 kHz. The experimental results demonstrated that the hierarchical variational autoencoder could be a strong zero-shot speech synthesizer, given that it outperforms LLM-based and diffusion-based models. Moreover, we achieved the first human-level quality zero-shot speech synthesis. Audio samples and source code are available at the project's website. Concept sliders, LoRA, adapters for precise control in diffusion models. We present a method to create interpretable concept sliders that enable precise control over attributes in image generations from diffusion models. Our approach identifies a low-rank parameter direction, corresponding to one concept, while minimizing interference with other attributes. A slider is created using a small set of prompts or sample images. Thus, slider directions can be created for either textual or visual concepts. Concept sliders are plug-and-play. They can be composed efficiently and continuously modulated, enabling precise control over image generation. In quantitative experiments comparing to previous editing techniques, our sliders exhibit stronger targeted edits with lower interference. We showcase sliders for weather, age, styles, and expressions, as well as slider compositions. We show how sliders can transfer latents from StyleGAN for intuitive editing of visual concepts, for which textual description is difficult. We also find that our method can help address persistent quality issues in Stable Diffusion XL, including repair of object deformations and fixing distorted hands. Our code, data, and trained sliders are available at the project's website. MagicDance, realistic human dance video generation with motions and AMP facial expressions transfer. In this work, we propose MagicDance, a diffusion-based model for 2D human motion and facial expression transfer on challenging human dance videos. Specifically, we aim to generate human dance videos of any target identity driven by novel pose sequences, while keeping the identity unchanged. To this end, we propose a two-stage training strategy to disentangle human motions and appearance, for example, facial expressions, skin tone, and dressing, consisting of the pre-training of an appearance control block and fine-tuning of an appearance pose joint control block over human dance poses of the same dataset. Our novel design enables robust appearance control with temporally consistent upper body, facial attributes, and even background. The model also generalizes well on unseen human identities and complex motion sequences, without the need for any fine-tuning with additional data with diverse human attributes by leveraging the prior knowledge of image diffusion models. Moreover, the proposed model is easy to use and can be considered as a plug-in module extension to Stable Diffusion. We also demonstrate the model's ability for zero-shot 2D animation generation, enabling not only the appearance transfer from one identity to another, but also allowing for cartoon-like stylization, given only pose inputs. Extensive experiments demonstrate our superior performance on the TikTok dataset. Sugar, surface-aligned Gaussian splatting for efficient 3D mesh, reconstruction and high-quality mesh rendering. We propose a method to allow precise and extremely fast mesh extraction from 3D Gaussian splatting. Gaussian splatting has recently become very popular as it yields realistic rendering while being significantly faster to train than NeuRPs. It is, however, challenging to extract a mesh from the millions of tiny 3D Gaussians, as these Gaussians tend to be unorganized after optimization, and no method has been proposed so far. Our first key contribution is a regularization term that encourages the Gaussians to align well with the surface of the scene. We then introduce a method that exploits this alignment to extract a mesh from the Gaussians using Poisson reconstruction, which is fast, scalable, and preserves details, in contrast to the marching cubes algorithm usually applied to extract meshes from neural sign distance functions. Finally, we introduce an optional refinement strategy that binds Gaussians to the surface of the mesh and jointly optimizes these Gaussians and the mesh through Gaussian splatting rendering. This enables easy editing, sculpting, rigging, animating, compositing, and relighting of the Gaussians using traditional software by manipulating the mesh instead of the Gaussians themselves. Retrieving such an editable mesh for realistic rendering is done within minutes with our method, compared to hours with the state-of-the-art methods on neural sign distance functions, while providing a better rendering quality. PhysGaussian, physics-integrated 3D Gaussians for generative dynamics. We introduce PhysGaussian, a new method that seamlessly integrates physically grounded Newtonian dynamics within 3D Gaussians to achieve high-quality novel motion synthesis. Employing a custom material point method, MPM, our approach enriches 3D Gaussian kernels with physically meaningful kinematic deformation and mechanical stress attributes, all evolved in line with continuum mechanics principles. A defining characteristic of our method is the seamless integration between physical simulation and visual rendering. Both components utilize the same 3D Gaussian kernels as their discrete representations. This negates the necessity for triangle tetrahedron meshing, marching cubes, cage meshes, or any other geometry embedding, highlighting the principle of what you see is what you simulate, WS2. Our method demonstrates exceptional versatility across a wide variety of materials, including elastic entities, metals, non-Newtonian fluids, and granular materials, showcasing its strong capabilities in creating diverse visual content with novel viewpoints and movements. Our project page is at project's website. PF-LRM, pose-free large reconstruction model for joint pose and shape prediction. We propose a pose-free large reconstruction model, PF-LRM, for reconstructing a 3D object from a few unposed images, even with little visual overlap, while simultaneously estimating the relative camera poses in approximately 1.3 seconds on a single A100 GPU. PF-LRM is a highly scalable method utilizing the self-attention blocks to exchange information between 3D object tokens and 2D image tokens. We predict a coarse point cloud for each view and then use a differentiable perspective endpoint (PNP) solver to obtain camera poses. When trained on a huge amount of multi-view posed data of approximately 1 million objects, PF-LRM shows strong cross-dataset generalization ability and outperforms baseline methods by a large margin in terms of pose prediction accuracy and 3D reconstruction quality on various unseen evaluation datasets. We also demonstrate our model's applicability in downstream text/image to 3D task with fast feed-forward inference. Our project's website is at project's website. NeuroPrompts, an adaptive framework to optimize prompts for text-to-image generation. Despite impressive recent advances in text-to-image diffusion models, obtaining high-quality images often requires prompt engineering by humans who have developed expertise in using them. In this work, we present NeuroPrompts, an adaptive framework that automatically enhances a user's prompt to improve the quality of generations produced by text-to-image models. Our framework utilizes constrained text decoding with a pre-trained language model that has been adapted to generate prompts similar to those produced by human prompt engineers. This approach enables higher quality text-to-image generations and provides user control over stylistic features via constraint set specification. We demonstrate the utility of our framework by creating an interactive application for prompt enhancement and image generation using stable diffusion. Additionally, we conduct experiments utilizing a large dataset of human-engineered prompts for text-to-image generation and show that our approach automatically produces enhanced prompts that result in superior image quality. We make our code, a screencast video demo, and a live demo instance of NeuroPrompts publicly available. GPT-4 Motion, scripting physical motions in text-to-video generation via Blender-oriented GPT planning. Recent advances in text-to-video generation have harnessed the power of diffusion models to create visually compelling content conditioned on text prompts. However, they usually encounter high computational costs and often struggle to produce videos with coherent physical motions. To tackle these issues, we propose GPT-4 Motion, a training-free framework that leverages the planning capability of large language models such as GPT, the physical simulation strength of Blender, and the excellent image generation ability of text-to-image diffusion models to enhance the quality of video synthesis. Specifically, GPT-4 Motion employs GPT-4 to generate a Blender script based on a user textual prompt, which commands Blender's built-in physics engine to craft fundamental scene components that encapsulate coherent physical motions across frames. Then these components are inputted into stable diffusion to generate a video aligned with the textual prompt. Experimental results on 3 basic physical motion scenarios, including rigid object drop and collision, cloth draping and swinging, and liquid flow, demonstrate that GPT-4 Motion can generate high-quality videos efficiently in maintaining motion coherency and entity consistency. GPT-4 Motion offers new insights in text-to-video research, enhancing its quality and broadening its horizon for future explorations.